Hello everyone, I'm Naoki Takisawa from Tokyo University of Technology. I would like to talk about distributed deep learning of ResNet50 and VGG16 with pipeline parallelism. There are two methods for distributed deep learning, data parallelism and model parallelism. In data parallelism, divided mini-batches are distributed to nodes. Each node places the whole network model on the GPU and processes its assigned data. When updating parameters of the model, all reduced communication is required to exchange the gradient data of each node with all nodes. Data parallelism is practical and generally used. However, data parallelism cannot train large model which cannot fit into a node. Model parallelism can be used for large models, as it divides the model into several submodels and allocate it to computation nodes. In both forward and backward propagation, model parallelism requires point-to-point communication. Model parallelism is difficult to perform efficiently due to the sequential execution of forward, backward, and model parameters updates. Therefore, it is important to make the model parallelism more efficient. Pipeline parallelism improves efficiency by pipelining processes. Pipeline parallelization methods are Google's gpipe and Microsoft's PipeDream, for example. In this research, we examine the effect of accelerating the pipeline parallelism by different of neural network models. In pipeline parallelism, it is required to divide the model and assign it to the computation nodes in the same way as in model parallelism. Intra-batch pipeline parallelism, like gpipe, the mini-batch is divided into micro-batches that are processed in smaller units. By increasing the number of mini-batch divisions, the overhead time of the pipeline shown by the blue arrows can be reduced. Inter-batch pipeline parallelism, like PipeDream, delays the backpropagation, thereby overlapping the computation of forward and backward propagation and improving processing efficiency. Parameter update use previous gradients. This affects the convergence of learning. In this research, we implemented data parallelism, intra-batch pipeline parallelism, and inter-batch pipeline parallelism. In data parallelism, there is no overlap of all reduced communication. In pipeline parallelism, the sending is overlapped and the receiving is not. First, we compare the number of parameters and the input data size of each layer for ResNet50 and VGG16. The number of parameters of VGG16 was 7 times greater than that of ResNet50. VGG16 has a smaller input data size than ResNet50 in all layers except the output layer. Next, we measure the communication time in both data and pipeline parallelism. We measure the time by communicating data of the same size as the actual data to be communicated. We took 100 measurements and compared the averages. The result of comparing the reduced communication time, VGG16 is longer than ResNet50. The results of comparing the point-to-point communication time, ResNet50 is 9.7 times longer than VGG16. Finally, we executed the training in data parallelism, intra-batch pipeline parallelism, and inter-batch pipeline parallelism, and compared the training time. We compare the results for ResNet50 and VGG16 respectively. We use 5 nodes connected by InfiniBand. The training data is a subset of 10 classes from ImageNet. The number of epochs was 20. As a result, data parallelism was the fastest on ResNet50. The intra-batch and inter-batch pipeline parallelism took 5.5 times and 3.3 times longer than the data parallelism respectively. The inter-batch pipeline parallelism was the fastest in VGG16. Both intra-batch and inter-batch pipeline parallelism took about half the time of data parallelism. This is because VGG16 takes a long time for all reduced communication due to the large number of parameters, and the point-to-point communication time is short. In this research, We compared pipeline parallelism and data parallelism using the VGG16 and ResNet50. We have experimented with models which can be executed on a single node to compare with data parallelism. For VGG16 having more parameters, the pipeline parallelism was 2.45 times faster than the data parallelism. For ResNet50 having fewer parameters, the data parallelism was 3.3 times faster than the pipeline parallelism. This is because data parallelism requires all-reduced communication for all parameters in each mini-batch process. For VGG16 having many parameters, all-reduced communication in data parallel takes time. For ResNet50 having fewer parameters, the data parallelism was faster because the overhead of all-reduced communication was relatively small. Pipeline parallelism is faster than data parallelism. When the model has many parameters, data parallelism cannot train a model which cannot fit into a node. Future work is developing methods for automatic model division. My presentation is over. Thank you for listening.